Hello everybody, welcome to Mr. Navarrete, and today I'll be going over the equilibrium constant homework number 1. So, let's get started. For number 1, it says, write the equilibrium constant expression for the following reaction. Now, what is our equilibrium constant? Well, our constant is a ratio that lets us know the rate at which our products and reactants are being used up. For our reversible reaction of nitrogen dioxide and dinitrogen tetroxide, we need to find what our equilibrium constant is. Creating our ratio between our products and our reactants, we can say that our equilibrium constant is going to be our concentration of dinitrogen tetroxide to the second power. This power comes from our coefficient in our balanced chemical reaction for our dinitrogen tetroxide. Now that we have our products, well, we need to create our ratio with our reactants, which will be the concentration of nitrogen dioxide, again, to the second power, as it has a coefficient of 2 in our balanced chemical equation. And this is our equilibrium constant expression. Let's continue doing this for the next reactions. For this reaction, if we want to find our equilibrium constant, well, again, it's going to be a ratio between our reactants and our products. Products are going to be on top, reactants in the bottom. So in this case, we get the concentration of B to the power of its coefficient B divided by the concentration of A to the power of the coefficient of A. For the reaction between hydrogen and iodine to make hydrogen iodide, our equilibrium constant is going to, again, be our products, the concentration of hydrogen iodide to the power of its coefficient, divided by the concentration of hydrogen, again to the second power for its coefficient, multiplied by the concentration of iodide. Same thing for this reaction. Well, for our equilibrium constant, we're going to put our products on top. We're going to get our concentration of sulfur dioxide and water divided by our concentration of sulfur trioxide and hydrogen gas. For our decomposition reaction of phosphorus pentachloride into phosphorus tetrachloride and chlorine gas, our equilibrium constant, again, we're going to put our concentrations of our products divided by our concentration of our reactants. For our reaction between hydrogen gas, chlorine gas to make hydrogen chloride gas, our equilibrium constant is going to be equal to the concentration of our products. Again, don't forget your power based on its coefficient, divided by our concentration of our reactants, concentration of hydrogen gas and chlorine gas. Next up, we have carbon monoxide reacting with oxygen to produce carbon dioxide. So our equilibrium constant is going to be equal to our concentration of our products, again, our power is going to be related to our coefficient, divided by our concentration of our reactants. For the reaction between sulfur dioxide, oxygen, water to produce dihydrogen sulfate gas, our equilibrium constant is going to be equal to our concentration of our products divided by our concentrations of our reactants. Up to this point, they've been pretty straightforward, but now let's look at the decomposition of water, liquid water, into its ions, hydrogen ion and a hydroxide ion. Again, our equilibrium constant is going to be equal to our concentration of our products. In this case, we can add divided by our concentration of our reactants. Now, why did I put a 1 for water? And that's because our water is going to have the same concentration regardless of changes in pressure, regardless of changes in volume, regardless of changes in temperature. Its concentration is going to stay the same. What we're observing are the changes in concentration between our hydrogen ions and our hydroxide ions, as our changes in pressure, temperature, and volume will greatly affect those. For our next reaction, we have carbon dioxide gas and water forming fructose and oxygen gas. Writing our equilibrium constant expression for it, we're going to get our products, oxygen gas, and that's going to be divided by our reactant, carbon dioxide. And again, I didn't include glucose, fructose, or water because, again, their concentrations are not going to change. They're going to stay constant. The major changes that we will be seeing are on our gases. Depending on our pressure, temperature, and volume, we're going to get different amounts of collisions affecting our rate of our reaction. On the back page, we're asked to calculate the equilibrium constants for the following reactions. The reversible reaction between nitrogen dioxide and dinitrogen tetraoxide. Let's focus on writing our equilibrium constant for it. Again, for our reaction, we're going to put our concentration of our products divided by our concentration of our reactants. Make sure to not forget your coefficient and to include it as a power where it belongs. I get an equilibrium rate expression of my concentration of dinitrogen tetraoxide divided by my concentration of nitrogen dioxide. And again, I made sure to include my power of 2 for my coefficient of 2. Now that we have our expression, well, we can calculate our equilibrium constant. We're given our concentrations at different times. So let's use that to find our equilibrium constant. For my first experiment, again, I'm just going to use my expression, and then I'm going to plug in the data from my table. For experiment 1, my concentration of dinitrogen tetraoxide was 0.595, and my concentration of nitrogen dioxide was 0.052. Plugging that into my calculator, I get an equilibrium constant of 220. Now let's do the same thing for our other two trials. Again, using my expression, plugging in my data from my table to get an equilibrium constant of 220. Last one, again, same expression, gonna use the data from my table and plugging that into my calculator, I get an equilibrium constant of, again, 220. For our last one, we are asked to find our equilibrium constant for the reaction between nitrogen gas, hydrogen gas to form ammonia. First thing I'm going to do is write my equilibrium constant expression. I'm going to have my concentration of my products, so ammonia, again to the second power for its coefficient, divided by my concentration of nitrogen gas times my concentration of hydrogen gas. Power of 3 is from my balanced chemical equation. Now that I have my expression, I can plug in the data from my table to find my constants. For trial 1, I just plugged in my data, and after plugging that into my calculator, I get an equilibrium constant of 0.0603. For trial 2, plugging in the data for experiment 2, and that into my calculator, I get an equilibrium constant of 0.0633. For my third one, I'm going to plug in that data from my table, and then that straight into my calculator to get an equilibrium constant of 0.0602. This is how we find our equilibrium constant. We only had to do 3 experiments so far, but chemists do hundreds just so that you don't have to. And that's going to be it. If you have any questions, don't forget to message myself or Mr. Morgan on Schoology. Other than that, stay safe, and I'll catch y'all next time.